Similarly, at origin point, it's the same thing. At origin, if you look at the direction or the length between the point and origin, it's just a 0. And that's why you're also getting a 0 from this formula. So this is a radial direction. Okay? Questions? Okay, so I want to give you one more very special vector field, which has a quite special picture. If this vector field is defined by -y and x, here the x component is defined as minus y. The y component is defined as x. I can still quickly draw the vector field together. Okay, so I still want to choose these points to be evaluated. So I want to find the vector field according to this formula. Yep.
Are you saying that those are functions, or?
Yeah, exactly. This is the function. According to the general formula, I'm saying f of xy is defined as minus y.
Negative, okay.
My gxy is defined by x.
Oh, okay.
Exactly. You can have more complicated formula, but the way of drawing the vector field picture is always the same. You put in a pair of numbers and then you draw a vector out. Okay? So for instance, at 0, 0, according to this formula, I'm getting a 0, 0. So I don't have, this is a trigger vector at the origin. At 1, 0, I'm getting, so this is not quite easy to imagine. So that's why, let's put them together. So if it is 0, 0, I have a vector 0, 0. So if I have a point 1, 0, what do we have? It's going to be 0 and 1, right? So 0, 1, this vector is pointing upwards, all right? This vector is pointing upwards. This is the vector. Okay? So at the point 1, 1, I have a vector which is minus 1, 1, and 1. So it's minus 1 and 1, so I have pointing upwards and pointing to left. So this is going to be the vector here. Okay? So at the point 0, 1, I have the vector minus 1 and 0. Is that right? Minus 1 and 0. So it is pointing to left. Pointing to left, this is the point. Okay? And at the point, say, minus 1 and 1. So the vector is given by minus y is going to give minus 1, right? And minus y is the x component. X is the y component. So I have minus 1 and minus 1. So the vector is pointing to left and downwards for both one unit. That's the vector right here. Okay? So at the point where x is equal to minus 1, y is equal to 0, the vector field is given by 0 and minus 1. Right? 0 and minus 1. So it is pointing downwards with one unit. Okay? So you can quickly draw all the pictures right here. This is going to be the vector here. This is the vector. And this is the vector. Okay? So this point is 1 minus 1. So according to this formula, the vector here is 1 and 1. So this is pointing up and pointing right. So this is the picture for the vector defined by minus 1 and x. The picture is pretty special. This vector field rotates counterclockwise. Can you see that? If you look at the overall picture of the vector field as a whole picture, these vectors are rotating counterclockwise with respect to the origin. All right? This vector field rotates counterclockwise with the origin. And this is the radial vector. Okay? So these two are pretty special vectors. Especially the first one, I want to give you a little bit more insights related to what we learned before. Okay, so if I look at this picture, this vector field is given by 2x, 2y. We actually learned about the vector fields before. when we learn about taking derivatives, there's one object very closely related to vectors. We take the partial derivatives, we can also combine them together to give you a gradient vector, all right? So that's where we learned a gradient vector before. So if I give you a function f(xy) is equal to 2x squared plus y squared, and I ask you what the gradient vector is, we use this notation for the gradient vector, all right? The gradient vector has two components. The x component is the x partial derivative, which is 2x. And the y component is the y partial derivative, which is exactly 2y. So we already graphed this vector field, but this vector field is not only special because it's a radial, but also it is special because it is a gradient vector of a function x squared plus y squared, all right? X squared plus y squared. Now I'm going to give you a very important link between the vector fields and the gradient vectors from the calculus point of view. When we take the gradient vectors before, this gradient vector has a very special property related to the function. You still remember the geometric relation between the gradient vector and function, where it is coming from. The gradient vectors are all perpendicular to the level curves, am I right? It's all perpendicular to the level curve. I even explained in plain words why it is believable, am I right? So if I look at this function, the level curves x squared plus y squared is equal to 1 or 2 or 3 at different levels. These level curves about this function are all circles, am I right? So now I ask you, what do we mean by a radial vector field? If a vector field is radial, it is exactly saying the vector field is supposed to be perpendicular to the circles. So if I draw a circle right here, these 4 points, 1, 2, 3, 4 points, these 4 points are exactly on the circle x squared plus y squared is equal to 1. These several points are lining a slightly larger level curve, all right? Because they are 1, 1, so this level curve is x squared plus y squared is equal to
root 2.
All right, so this is the level curve, x squared plus y squared is equal to 2. This level curve is x squared plus y squared is equal to 1. From calculus, we did learn the fact, a relation between the vector fields and level curves, no matter what function you have. As long as you have a function, you find the gradient at every given point, you can always compute what the gradient is. The gradient vector is always perpendicular to the level curves, all right? And in this special case, because the level curves are all circles, if you have a vector field to be all orthogonal to the circles, this vector field has to be radial. That with me? This vector has to be radial. The whole point for a radial vector field is, given any point, you can line the center and this point together. This is the radial direction. And if the vector field at this point is also radial, it has to be perpendicular to the circle at this given point. All right? Know with me? So this is the one. If I look at this function, the function we had before, f is equal to 3x and y. I'm saying this is also a gradient vector of some function. I'm saying this is also a gradient vector of some function. Can give me the answer of the function. I only have x squared divided by 2 multiplied by 3. And I want to have half of y squared. So f xy. If my f xy is equal to 3x squared divided by 2 and y squared by 2, and then I take the x and the y partial derivatives, this is going to be the gradient vector, exactly. And this is a function involving 2 independent variables. If I look at the level curves for this function, what do you think the level curve should be? It's not going to be exactly circle as x squared plus y squared like here. It has different coefficients, so this is going to be a elliptic, right? So 3x squared divided by 2 plus y squared divided by 2, for instance, if I make it equal to 1, I say this defines an elliptic because this is x squared divided by 2 2 divided by 3 plus y squared divided by square root of 2 squared. So square root of 2 squared is equal to 1. So this level curve actually defines an ellipse with x-axis square root of 2 divided by 3 and y-axis square root of 2. By changing different values at different level, you're getting different ellipses with different sizes, all right? Just very similar as the center over there. At this point, the level curve is a family of circles. These level curves is a family of ellipses. And I'm saying this vector as a vector field, but also a vector coming from a gradient vector of a function, should also have the property. These guys are all perpendicular to this family of ellipses, all right? So this is a very important connection, which you can explain by calculus. If your vector field is coming from a gradient vector, then this vector field has to be always orthogonal to the level curves defined by its parent function. Are with me? Defined by its parent function. I have one big remark to make. The parent function has to be a scalar function, whereas the gradient vector is a vector field. Are with me? So this is a function which is a scalar function. A scalar function, if I put in a pair of numbers, I'm getting a number, whereas its gradient is a vector field. Okay? If I have a vector field, and this vector field can be written as a gradient vector of some scalar function, this vector field is very, very special. We call it a conservative vector field. And this kind of conservative vector field in calculus is the easiest starting object. So I will give you plenty of properties on the vector field, which is conservative. Equivalently, I'm saying it is a gradient vector of a parent function. Are you with me? Okay, so this is a conservative vector field. This is also a conservative vector field because I can find its parent function as a scalar function. You know what I mean? I want to ask you a very interesting question. How about this vector field? How about this vector field? Can you find its parent function if there is such a function?
That would be hard to do.
Right? If I want to find a small f such that the x derivative is equal to -1, the y derivative is x. If I want to have x derivative to be -1, I really want to have minus x1. Okay, right? So that if I take the derivative of x, I get a -1. But unfortunately, if I have this function, I take the derivative with respect to x, with respect to y, I'm supposed to get a x, but I'm getting a minus x from this function. So you can try to fit in what function you can have, but it is not even possible to find such a parent function, such that this vector field is exactly a gradient vector of some parent function. So one big object we're going to study is to give any vector field. Our first job is to determine whether it is a gradient vector. This one is not a gradient vector. Both of this and that are gradient vectors. This one is not a gradient vector. I will give you one criteria to exactly see why it is not a gradient vector. And if it is a gradient vector, we want to find a uniform way to find its scalar parent function. Are you with me? So this is one of the very important topic in this calculus involving vector fields. So I give you these different examples, but I don't want you to be very restricted by these easy functions. I can give you plenty of seemingly more complicated functions. For instance, I have 2e to minus x and 0. Okay? This is also a vector field, where the x component is defined as a function 2e to minus x. Y component is constant 0. This one, even the x component is slightly more complicated than before. Y component is super easy. So if I want you to have a mental picture of what this vector field should look like, because x component is always positive, then this is always pointing to right. Y is always 0, so you don't have to have any y component. And this vector field should be always pointing to the right direction. And when x is tending to past infinity, the x component is going to 0, all right? And when x goes to negative infinity, this component is getting larger and larger. So you're going to get a field of vectors where in here it's very small, and here you're getting slightly larger, and it's getting longer and longer, but all of them are pointing to right. So these vector fields, depending on what functions, what formulas you're getting, you're supposed to have different pictures of the vector fields. No matter what vector field you're getting, you can always draw the picture by choosing the sample points, as what we did throughout the lecture, all right? You can choose a list of sample points, and given each one of them, you find a vector, and then you draw the vectors at different base points. That will be the picture. That's the first thing I want you to be able to do. This is a pretty easy part. The second part is slightly harder. I want you to have a mental picture without even drawing to understand some properties of the vector fields, okay? Especially this one and that one, okay? This is a pretty easy one, right? As long as the y component is equal to 0, it has to be parallel, right? It has to be horizontal. X is always positive, and I know it's pointing right. And x is increasing, the x component is decreasing. So that's why I have this vector to be getting shorter and shorter when x goes to positive infinity. Are you with me? These two are always there as well. So this is a radial vector field. So you should have a mental picture of what a radial vector field should look like. It's spreading from the origin pointing to the same direction as the radial direction. And this one is a rotating vector field. It is rotating counterclockwise. I want to ask you a very interesting question again. How do I make it clockwise? How do I make it clockwise? Think about that. How do you make it clockwise? Okay. So, any questions before we move on to the next section? In the first section, it's pretty easy to just understand what the definition of vector field is, how do you graph it, and if you don't even graph it, how can you understand some basic properties of the vector field, right? Like the one I just stated here. So one thing you have to always keep in mind, the vector fields, the objects are basically vectors. Okay, so remind yourself constantly, always put this